Okay, we are recording. So yes, this handout we had on sets, hope this link is right. Open, actually it's gonna open, I need to change the share to this thing. Yeah. Okay, so we had started, most of the groups kind of got through number 1 and 2. But maybe we can just quickly remind ourselves what we figured out. And I might try to write things a little carefully just because we're going to talk about quantifiers later today in class, and I want to, these could be good examples of quantifiers. So let me actually, go to the board and just talk through some of these real fast. So, that handout. That handout, number 1A. So one thing I had neglected to mention explicitly last time, or at least right on the board last time, is that we have all these sets, right? We have like Z for the integers and Q for the rationals and R for the reals. N is the set of whole number counting numbers. Whenever I refer to N, that's what I'm talking about. I'm actually going to give you an axiomatic definition of this at some point as it lives inside it's a subset of the integers. So this S right here, where we're taking the integers such that, remember we read this as like such that X is prime and X squared is less than 50. So did you guys, one thing I also didn't say about group work maybe is that like, it's nice to sort of rotate who's at the board and like so other people can write stuff down in their notes. So I don't know if you guys wrote this down, but these are just the positive numbers whose square is less than 50, right? So what were they? 1 is not considered prime. We'll talk about why at some point. It's the primes that are whose square is less than 50. So just 2, 3, 5 is not prime. Okay. So that's just a way of saying 2, 3, 5, and 7. I threw some ors and let's see. So what was T? X is prime and either X is even or X is between 10 and 30. So what did you guys say for that? I may not copy the whole thing from the handout. I'll just, and these are natural numbers. So positive numbers that are numbers prime and either X is even or X is between 10 and 30. So what numbers satisfy that? Two satisfy. So two fits right. 2 is prime and 2 is even. Okay, and then what else? So 11. So then you just list the primes from 11 to 30, right? I think that's what that was. Good. Yeah, what is U? Yeah. Yeah, just negative. So there's no restrictions except negative. It's not prime anymore, but okay. Yeah, this is kind of interesting because this is the X and Z so that you can find a Y so that X squared plus Y squared is less than or equal to 25. So what integers does that end up being? Yeah. Did you have? 0, 3, 4, and 5. Those could get you to exactly 25, right? I mean, so if you were looking at the set here, you'll write it this way. There is a y in z such that x squared plus y squared equals 25. Let's say v alternate b. If that was equal 25, then right, I think you would have, what did you say, 3 is 3 squared plus 4 squared is 25, 4 plus 4 plus 3 squared is 25. What else did you say? Yeah, because 0 squared plus 5 squared is 25 and 5 squared plus 0 squared is 25. So you could actually have 0, is that it? Yeah, so you could actually have plus or minus, if it was like that. The actual v that we have, where it's all the same except less than or equal to, what satisfies that? So all these same numbers are in it, right? But what else?
-4. Yeah.
We
Plus
have
or
those.
minus 1, 2, 3, 4.
Yeah, so we also can throw in, yeah, plus or minus 1 is fine too, right? Like, because 1 squared plus any is, yeah, 0. There is a y, so that makes this less than or equal to less than 25. Good, so just like plus or minus. Good. Okay, so that somehow picks out those numbers. Maybe a slightly more interesting thing is to try to write the answers to number 2. And I know I threw a lot of you off with 2b. Nice pattern. So A was just, yeah, how would you say this? The integer is such that, what? What are the conditions that we give? Even and greater than or equal to 0. -10 is considered even, if you want to, because you can factor a 2 out of it, right? So such that n is greater than or equal to 0, and n is even. You could say here, instead of saying n is even, you could say there exists a k such that n equals 2k or something like that if you wanted to. So you could also replace this with like, or there is a k in z such that n equals 2k is the way you could write that, right? Now, what was the pattern in B? Yep, good, right. So they were one more than the squares. That was a pattern. So B was, yeah, the set of, for some reason, this is another like math cultural thing. I think of X and Y as like continuous variables, and N and M as like counting like whole number variables. It's not, of course, like the symbol doesn't matter, but it's just kind of a thing. So I tend to write N or M or K or something. So let's just say N and Z such that, there's a couple ways you could write this. You could say there is a M such that N equals M squared plus 1, or you could say N equals M squared plus 1 for some choice of M and Z. So sometimes that we rewrite the language that way too. Like it's slightly more readable, maybe, Yeah.
Is there a subset of the integers that is the natural numbers?
Some people like to call that natural numbers, they like to include 0 in the natural numbers. So that's sort of like some books you'll see it with 0, some books without 0. You could write just natural numbers union 0 like that, or you could, some people will write things like this, or instead of the natural numbers, they'll just write that, or like positive integers and greater than equals 0. So you'll see notations like that, but yeah. Was that part of the board on screen? Not really. There you go. Okay. I want to write over there. All right. So yeah, so you can say it this way, or you could say, I guess the slightly more formal way would be, or I mean, we're going to talk about the existential quantifier today, because we always say like there is. We say there exists or there is a lot. So I'm so tempted to just write the symbol. It's a backwards E symbol, but we're going to talk about that. So there exists. I'll say it that way. There exists M and Z such that n equals m squared plus 1. I mean, I think some like people who want to be really pedantic would balk at this because we didn't introduce the letter M before we used it. It's again a very subtle, a very mild point, not a very big deal, but if you want to be like that, you can. So C and D are similar, right? What's everything in C? Part C. What are these numbers? Yeah. 4n plus 1, 4k plus 1, 4n plus 1. Yeah. So these are this such that n equals 4m plus 1. Well, actually, we also should say n is greater than 0. Because like -3 is of the form 4m plus 1 and stuff. So n is greater than 0. And so I could have just said, so there's actually a different, maybe I'll write this, there's different ways to say this. And n equals 4m plus 1 for some m and z. We could have said, instead we could have just said n in the natural numbers such that n equals 4m plus 1. Some m, I guess that's also in the natural numbers, but it doesn't really matter. There are sometimes people will just write things like, there's another notation, I'm not sure the book mentions this, but you see it sometimes. I don't love it as much, but you can kind of see what they're saying. Actually, how about this? I'll do, you suggested. I got to start learning names. What's your name? Colin. Okay. So you could, there are books that will write stuff like this, or people will write stuff like this, which is kind of a weird, this is sort of an alternate way of writing things, which is basically saying like list everything in the form 4m plus 1 as m runs through all the numbers from 0 to infinity. Everything of the form 4m plus 1 as m sort of runs through all, yeah, all non-negative integers or something like that. So that's another way that sometimes you'll see stuff written. Oops. Because that was like, so that's an alternate sort of way of writing things down. Does that make sense? You can see both, yeah. Or, like here before the vertical bar. Yeah. But well, so okay, I think in that case, it would be like you're listing both n and m, whereas here we're just listing n.
Yeah.
Like we're not listing the numbers.
Yeah, or right
like this stuff before the vertical bar is like the stuff that we're listed, like,
I see.
and this is the condition.
Okay, that makes sense.
Does that make sense? No, I like the question because it's like, I mean, yeah, a lot of it's just conventional, like how we write stuff, but then there usually are some reasons, you know. So, okay. Yeah, so this is just an alternate notation that some people like to write. I mean, it's a little more compact, right? So people like that. Okay. Oh, and then D. I guess the only thing to say about D is that we have to say that we're in the rational numbers instead of in the integers. So D is the set. I'll use X now in Q, such that X is 1 over n for some n and the natural numbers. Is that right? Or you could just write, like you said, 1 over n. I didn't even notice say this is not, I mean, an integer because it's actually because n runs through the natural numbers, that means 1 over n lives inside the rational numbers, you know. So those are some different ways to write that. So I mean, when we're being sort of formal in this class, we probably want to write stuff like this just because we're going to be doing lots of, but you know, when you're doing math out in the real world, when you're doing your math and you're writing your sets down out on the streets, this is math on the streets right here. Okay. Good. So let me just remind myself of things I wanted to say. Oh, okay. So like, there's some other problems I'm going to let you guys work on, but I do want to say a few things because they're also related to some of the problems down here. So yeah, I'll just leave that up there. I'll see where I'm trying to go with stuff. So we said complement, right? So I do want to start drawing pictures of sets with Venn diagrams, which is, I'm sure, something you've seen before, but it's can be helpful. It's not really a proof, but it can be a helpful illustration to like lead you to proofs and stuff. But and one thing the book sort of talks about, which is sort of useful to think about, is like a lot of times we're in some larger set. Like all these sets of numbers could be considered to live in like within the real numbers or even within the complex numbers. So there's some like universe. So then we would have some sort of like, I almost want to say there's some sort of like universe, sort of universal set U. And then within that, we could have like an A, like a set A, right? That we represent as like a bubble. It's probably not unfamiliar to you. You have another set B, but what I want to mention is that we have, this is A, this is, everything outside of this is what's called A prime, the complement. Some books will write a little C up here instead. Again, there's just different notations you see for these things. And so we could define A prime to equal all X in U such that X is not in A, right? I have another notational thing here, which is when I define something, I often write colon equals. Not every book does this. I sort of like to do it. Some books do it, and I like to do it because it reminds me that this is the definition of this thing, the symbol. We're actually telling you what this symbol means. Some equalities just mean like, you know, X equals 5. If I saw some equation, I end up with X equals 5, then that's just an equality, right? But here, this is like saying more. It's like saying whenever I say A prime, what I really mean is this. So this is defined, or maybe is defined to be the colon equal sign. Okay, so we define A prime as this. Does that make sense, right? Just everything outside of the set. Now then the question I wanted to talk about was like, how do we prove? A lot of times you want to prove that one set's a subset of another set, or really you want to prove that two sets are equal, right? So, so let me throw another set in here. B. So that's your kind of standard Venn diagram you're used to looking at. So, but A prime was, maybe I should say, yeah, A prime was everything outside of A. So including the stuff that's in B, but outside of A. Right, so question. How do we prove two sets are equal? Well, the idea is if we have two sets S and T, S equals T if and only if, remember is another way of writing the double-headed arrow, the logical limit. If and only if S is a subset of T and T is a subset of S. That is a way to sort of, we want to prove two sets are equal, we say the first is contained inside the second and the second is contained inside the first. Does that make sense? And then how do we prove something like S is a subset of T? Well, this is saying like for all X in S, or maybe I should just say this, like X is in S implies X is in T. That's what it means to be a subset, right? So we can actually break these down to logical statements. Right, so to prove S is in T, we just want to show every element of S actually lives inside T. So that's what something like this means. And then actually this reverses it. So you could also say that you're just trying to prove that X is in S if and only if X is in T. Right? These are all sort of different ways of saying the same thing. But a lot of times when we prove this, we sort of prove in both directions. We prove this statement and we prove this statement. So the example I wanted to do, and then there's another example on the handout that you guys can puzzle through and go back into group work in a minute, is what if we think, let's see, what did I put there? A union B prime, right? So if we take, maybe I will draw this schematically, right? A union B prime, I claim, well, let's draw it. So here's A, here's B. A union B is, yeah, what part of this represents A, the complement of A union B? Yeah, it's all of, that's A union B, that's the complement of A union B, right? And I'm claiming that that's the same thing as the intersection of the complement of A and the complement of B. Right, so A prime intersect B prime. Now let's see, do we believe that? Maybe it's worth drawing this twice and then intersecting and seeing if we get. So A prime is that, right? And B prime is that. I should write A and B. Do you agree if you only take things that are in both of these, then you actually get everything there? A little weird, but it's like, yeah, you're intersecting these. You're intersecting all the green stuff and all the blue stuff. And yeah, I don't think people write this, but I could write like that. Nobody writes stuff like that, but you know, yeah.
Prove that from
Yes, exactly, actually, because there's those like De Morgan laws. I think it proved one of them on the problem set. I don't remember if it was this one or the flipped one. But yeah, exactly. So, so proof. Let's show each one's contained inside the other. I mean, there is some way to do it all with if and only ifs, but I kind of just because I want to like show the steps. So let's show. So one way you'll see the proofs written is like, well, let me just say it like this. So let's show A union B prime is a subset of A prime intersect B prime, and A prime intersect B prime is a subset. Actually, I tend to want to write this the other way around. So A and A union B prime. You can flip this symbol. So let's prove both of these statements. And so what you'll often see when people write proofs is they'll do something like this, like this is the part of the proof where we prove that the first set's inside the second set. Like that we prove the subset this way. Okay, and the way you're going to do it is you're going to let X be any element of this. So these are the kind of proofs you can sort of follow your nose on, but Holland. Okay, sorry, I forgot your new word. So, but we're getting the key step's going to be what Colin just said about like the De Morgan law thing that we. So if X is in A union B, the complement of A union B, and we just sort of want to follow steps until we can get that X is in A prime intersect B prime, right? Like that's what we want down here at the end. But we want a bunch of logical steps to get there. And so this means, what does it mean to be in the complement of A union B? Well, that's interesting because that's almost what we're trying to prove, although it actually is going to be and. But I want like the most basic step is just to say what prime means, right? The first thing is just to say that means X is not in A union B by definition. And I do think you can sort of think about this as a negation of a logical statement. You can also think about this or the negation of the statement X is in A union B, right? That's the negation of that statement, which is, we can now break this up as the negation of X is in A, like the definition of union is an or, right? It's a logical or X is in B. So we can reduce, like X being in A union B complement to be translated into this logical statement right here. And then, so this is like a P and a Q, right? And it's like the truth table things that we did. And so what did you show? Again, I can't remember if you showed this one on the problem set or this with the and. Anybody remember? I assigned one of them. Didn't I assign one of them on the problem set? Does it look familiar? No? Did I assign it on the problem set? You see some nods and some blank looks. But if you wanted the negation of P or Q, like when is P or Q not true? Yeah, sorry, I'm gonna say, yeah, like it's basically you need P to not be true and you need Q to not be true, right? And we actually, you can show with the truth tables, like I thought I made you show one of these on the problem set, but you can show with truth tables that those are the same. You get the same truth tables, so they're tautology. So this is the same thing. As, right, X is, yeah. And this is called, these are called De Morgan's laws, just about how negation distributes over, like basically negation turns or into and it turns and into or. We're going to talk about negating logical statements pretty soon also. So, Thus, we have the negation of X is in A and the negation of X is in B, right? Which is the same as X is not in A and X is not in B. Which is the same as X is in A prime and X is in B prime. Equivalently, X is in A prime and X is in B prime, which means X is in A prime intersect B prime. Okay. Yeah.
From the not X in A or X is in B to the next one.
That's right. Because like this is not the negation of P or Q, which is equivalent to not P and not Q. Yeah. I'm gonna just say by De Morgan's, by one of De Morgan's laws. I don't even remember that they're called this, but yeah. Okay, makes sense. And then you'd want to prove the other direction, which is starting in here and going backwards until you got X is in A union B all prime. I'm not sure. The steps are actually exactly the same because I think they're all reversible. You could write this as a chain of if and only ifs. So, so that proves the subset that way. So then you could also say this, and you could say let X be in A prime intersect B prime, and then you want to do a bunch of steps and end up with X is in A union B. Right. And I'm not going to write it all out because I think basically you would go backwards in every step pretty much. Which sometimes it's not bad to check, but you could also just chain a bunch of if and only ifs together. Like X is in here, if and only if this is true, if and only if that's true, if and only if that's true, if and only if that's true. You have to check that they're all reversible, but you know, you could write it as a chain of if and only ifs if you wanted to. Because that would sort of prove directly this thing right here. Okay. Just saying there's different ways to write proofs, but it's not bad to do it this way too. It's just at some point you might be like, oh, I'm doing the exact same steps, just in reverse order. Okay, cool. Yeah, okay, the only thing, I'm gonna let you guys work in groups a little bit, and then we'll come back and talk about quantifiers. We'll just play with the groups. I just want to break up the class, so we'll do the work just for another 15, 20 minutes or something, and then, but I did want to say, I think one of the questions with the quantify and on the set handout is I didn't define the set difference. Because some people would like to only do this if B is a subset of A, but here's a more general definition, which is basically if I have my A and B here, then A minus B is this piece, right? That like crescent moon shape right there. So A minus B is defined to be the set of X in U. The set of X in whatever our universe is, such that X is in A and X is not in B. Okay, so that's just the definition of the set difference. You're sort of taking out anything. You're looking at A and you're taking out anything that happens to also be in B. Cool. Okay. So yeah, so like 4 and 5, I think especially are kind of things that we just kind of talked about. So you might, you could spend a minute on 3 if you want, but I would really look at 4 and 5. And so can we go back into groups and look at 4 and 5 for maybe 15, 20 minutes, and we can come back together and talk about quantifiers for the last 20 minutes. Let's do it. All right. I will pause the recording. Let me share the screen just so. Yes, you may. Right, so if you're watching the video, just do number 4 and 5, but I'm gonna pause the recording.